which has lone pair, that will show plus M effect. So I'm gonna show you the resonating structure. As you can see, this will be our resonating structure. This will have negative charge. There will be double bond and then OH and then again positive. And the rest part will be as it is. Now, if you are going to move from this to this side, so you can see this will be the scenario. Negative charge will come here and the rest part will be as it is. And then again, if you're going to move this charge to this side and this charge to this side, the bond, then you can see this will be the scenario. Negative charge moves to this negative becomes double, and double was there and double was there already, and this is your OH positive. Now if this will move to this side, this will again move to this, and you will be getting this. And you can see this is your double bond, double bond, double bond, and OH. So these are all resonating structure of phenol, which is hypothetical. But if you want to draw a real structure, that is known as resonance hybrid, so you just need to draw in the same way. You just need to show the single bond, and wherever the double bond travels, you just need to show that. And there was single bond, OH was there and it was traveling. So there will be delta positive, then comes delta negative here, then comes delta negative, delta negative. So this is your resonance hybrid of this phenol. All I want to ask from this, if everyone knows what is electrophile. Electrophile is an species which is having deficiency of electron. So if any electrophile you can take here, what do you think in this compound, where will this E plus electrophile will attack? What do you think with respect to this? You know, this is OH, so this will be your ortho, this will be your meta, and this will be your para. Again, this will be your meta, and then this will be your ortho. What do you think? This electrophile will attack at which position? Ortho with negative, on meta, on para, on meta, on ortho. What do you think? Any answer, Alan? What did you say? Para?
Yes, sir.
Okay, wrong answer. See, don't go for the obvious reason like you have seen the reaction, the major product is para. What I asked, this is positive charge, or you can see that this is the species which is having deficiency of electron. That means it requires or it needs electron. So it will definitely attack on ortho position in this condition only. I'm talking about the first condition, because on ortho position, it has negative charge that represents it is having electron rich. It is electron rich. That's why this electrophile will attack on ortho position in this condition or in this diagram or resonating structure. But when you are going to talk about this, then it will attack on para. And if you are going to talk about this, then in this, it will attack on para. All I want to say is that this OH, which is plus M group, which is directing the electrophile to attack either on ortho or para, not on meta. Because you can see during resonance, there is no charge on meta position. That's why the resonance at meta or the contribution of resonance on meta position is 0. Is that clear? Electrophile will always go to the nucleophile. And what is nucleophile? Nucleophile will either have a lone pair or will either have a negative charge. That's why this plus M is also known as ortho and para directing. Ortho and para directing. Is that clear? Please do let me know. Bharat, Alan, Saif, Mamuna, Hanifa.
Yes.
Yes, sir.
Now we are going to talk about this M. And you know what I told you? If any species that is connected with double bond and having lone pair, that will be acting as minus M. These are all tricks to understand. You don't need to remember which one is plus M and minus M. Singly bonded lone pair plus M. That means that will give electron to the benzene ring and it increases electron density in benzene ring. Who increases? Plus M. But when you are going to talk about minus M, electron density decreases. Electron density decreases by this minus M. And how you are going to recognize doubly bonded and having lone pair? So you can see doubly bonded. It will attract its electron. Then this will move to this side. So now you can see this is your benzene. So there will be double bond, then C, then single bond, O negative, and then H, and there is a wait a minute. Yeah. Everyone is able to see the screen now.
Yes, sir.
Yes, sir.
Okay. Now see, there will be a positive charge, and the rest part will be as it is. Now you can see this will move to this side, so the positive charge moves to the para position. Everyone understand or recognize whether is para and whether is ortho and meta, right? If you still have any confusion in that, please do let me know. This will move to this side. So double bond moves here. There is a double bond. Positive charge comes here. Doubly bonded C, O negative, and then H. And again. This moves to this side. So this moves to this side. And C, double bond O, and then H, double bond this. These are all resonating structure. Now, if I want to draw the resonance hybrid, it's very easy. You can see. I just need to show the single bond. Now you can see double bond is started. Initially, double bond was here, then it comes here, then here, like this. And there was also delta negative, then delta. This is the what? This is what? This is basically your resonance hybrid. Is that clear? Yes or no? Please do let me know.
Yes, sir.
Yes, sir.
Now I'm going to ask you a question. Again, in the first case of alcohol, which has a plus M effect. Now, if I'm going to take an electrophile and I want to substitute this electrophile in the ring, not outside the ring, on the ring, basically on the ring. So on which position this electrophile will attack? Ortho with respect to this CHO, ortho, meta, para, meta, ortho. On which position this electrophile will attack? I'm talking about all this canonical structure. Can anyone tell me? Yes or no?
Para.
I'm not actually what I want to ask is that in all of this, I want to ask, what do you think about the attacking of this electrophile in all this, three? Think about it. See, electrophile is electron deficiency. First, if you want to go and attack on this position, there is positive charge that represents it is already having deficiency of electron. In the second, you can see On para, it is also having electron deficiency. And again on the third, you can see on the left para, on the left ortho, it is also having the deficiency of electron. So only one position left, that is meta. At least it is not electron rich, but at least it doesn't have positive charge. It is not facing any kind of deficiency of electron. So this minus M is known as meta directing. Due to this minus M, it decreases the electron density in ring, especially at ortho and para position. That's why you can see positive charge on carbon, that is having deficiency of electron at ortho, then para, then ortho. Only the meta position left, not with negative charge, not with too much electron, but at least it doesn't have positive charge. That's why this minus M is known as meta. Meta. Is that clear? Can you change the slide? Please do let me know. Can I change the slide? Saf, Mamuna, Farhad.
Yes, sir.
Okay.
Yes.
Now moving to the next, I just wrote whatever I explained here. All plus M group for benzene is activating. Why activating? Because plus M increases the electron density in the benzene ring. And this plus M are ortho and para directing, because there will be negative charge on ortho and para. That's why electrophile will come and attack on ortho and para. And we know that para is more major product because it is more stable than ortho, because there will be a steric hindrance. You know that. The next is about minus M, and you can see all minus M is all minus M for benzene ring. Deactivating. Why it is deactivating? Because it withdraw electron from the benzene ring and the electron density decreases in the benzene ring. And you can see it is meta direction as meta directing, as you saw that there was positive charge on ortho and para, so it directed towards meta. That's why this minus M are known as meta directing. Is that clear? Can I change the slide? Bharat, Mamuna, Saif, can I change the slide?
Yes.
Now moving to the next topic. The next topic is aromatic, non-aromatic, and anti-aromatic. How you are going to classify the compounds, either whether the compound is aromatic, non-aromatic, anti-aromatic. So there are 4 rules to decide whether which compound is aromatic, anti-aromatic, and non-aromatic. The first one says that the compound should be cyclic. The first condition is compound should be cyclic. If a compound is not cyclic, that means it is non-aromatic. How? See, first of all, you need to take care of this. Either of 4 rules, either one of the 4 rules failed, then it is non-aromatic. It is non-aromatic. चारों में से कोई भी एक फेल हुआ, that means it is non-aromatic. Is that clear? So compound should be cyclic. Then the second condition is compound should be planar. Compound should be planar, and for planarity, carbon should be either sp hybridized or sp2 hybridized. Then comes the third, compound should have complete conjugation. If the compound is compound is cyclic, planar, then go for the complete conjugation. That means resonance is taking place inside all the ring, everywhere in the ring. That is called conjugation. And then comes your Huckel rule. Now see, Huckel rule here is of 2 types: 4n plus 2 pi electron, and here comes 4n pi electron. This is for anti-aromatic and this is for aromatic. If all 4 all four rules or condition, all four conditions are fulfilled, then you will be going for the Huckel rule. And what is this? Basically, n equals to 0, 1, 2. Whole number, it is whole number. Like if you are going to put the value n is equal to 0, you will be getting 2 pi electron. If you are going to put the value 1, you will be getting 6 pi electron, and so on. If you are going to put the value 2, you will be getting 10 pi electron. So, and here n is equal to natural number 1, 2, 3, 4, 5, and so on. N will be equal to 1, then that means 4 pi electron. It is multiple of 4, or the table of 4, you can say 8 pi electron, and n is equal to 3, that means 12 pi electron. Now, I'm gonna take this example. This benzene ring, everyone is aware of this benzene ring. So benzene ring is this, like this. So if you are going to check whether a compound, this compound is aromatic or not, so what you need to do, first check it whether it is cyclic. That means you are going to write it cyclic, and it is all done. Then you are going to check the planarity. So if you are going to check the hybridization of each carbon is doubly bonded. That's why this compound is planar. Second condition satisfied. Now you are going to check the conjugation, whether the resonance is taking place in all over the ring or not. So you can see conjugation is there, pi sigma, pi sigma, pi sigma, they are in complete conjugation. That's why conjugation is also satisfied. Now the last one is pi electron. How many pi bond in benzene ring? 3 pi bond. 3 pi bond, you know, in one bond 2 electron, so 3 pi bond, that means 6 pi electron, and you can see 6 pi electron comes in this part. That's why this benzene ring is aromatic compound. Is that clear?
Yes,
If
sir.
any one of the four rules is violated, then it is non-aromatic. Now come to this. Come look at this, like this and this. Now you can see cyclic. Yes, it is cyclic. Planar. Yes, it is planar. You can see every carbon, 4 carbon is in the ring, and every carbon is sp2 hybridized. That's why it is planar. Conjugation. Yes, complete conjugation is there. Conjugation is there. Then come for the Huckel rule. After this, you are going to count the pi electron. How many pi bond is there? 2. So pi electron is 4 pi electron. You can see 4 pi electron. That means it is anti-aromatic. Is that clear? Hmm. Now, if I'm going to ask you a question like this, you can see. First of all, cyclic. Yes, it is cyclic. Planar? No, not planar. Not planar, because this is sp2 planar, this is sp2 planar, but this is singly bonded, which means sp3 not planar. That means this is non-aromatic. Non-aromatic. Is that clear, everyone? So there are four rules to decide the aromaticity. Compound should be cyclic, compound should be planar, compound should have complete conjugation in the ring, and then Huckel rule. If it is having 2 pi electron, 6 pi electron, 10 pi electron, 14 pi electron, 18 pi electron, that is aromatic. And if it is having table of 4 pi electron, 8 pi electron, 12 pi electron, 16 pi electron, 20 pi electron, then it is anti-aromatic. And if any one of the four rules violated, then it is non-aromatic. If anyone have any doubt regarding this, please ask me. Any doubt? Mamuna, Farhat, Saif?
No, sir.
Okay. So I'm gonna give you some question. I'm waiting. Now I will be able to understand. You just need to write in chat box one. See, for aromatic, you are going to write 1A. For anti-aromatic, you are going to write number of the question AA. Non-aromatic NM. Don't write all the name. Okay. Okay. I'm waiting. H is H. Hanifa or someone else. Okay, Hanifa, you are very good. That's good, Saf. Further, any answer, Mamuna? Saf, please do remember the sixth one is wrong. I will explain it, okay?
Okay, sir.
Up to fifth, you are correct. Alan, any answer? Hanifa? Farhat, no answer at all. Okay, I'm gonna explain. See, first rule is violated. This is not cyclic, so non-aromatic. This is your cyclic, but when you are going to check the planarity, it is not planar because this carbon is sp2, this carbon is sp2, but this is sp3, which is tetrahedral. So second rule is violated. That's why it is also non-aromatic. This is your cyclic. Planarity, you can check all the carbon. You need to check only inside the carbon. Outside the carbon, what happens, that doesn't matter for you. Okay. All the carbon is sp2. That means it is planar. You can see it is complete conjugation. So conjugation is there. So it is complete conjugation. And 6 pi electron is there because 6 pi bond is there. And hence it is aromatic. Come to the next one. Cyclic, planar, conjugation, and 6 pi electron. So it is also aromatic. Come to this cyclic, it is planar, it is sp2, sp2. This is also your sp2. Conjugation, complete conjugation, you can see pi sigma plus pi sigma vacant orbital. So complete conjugation, cyclic, planar, and 2 pi electron. That's why it is aromatic. So focus here. Six, question number 6. Cyclic, it is planar, it is. Why it is planar? Because you are not going to take this in hybridization and make it sp3. It is sp2 because this negative charge is in conjugation with this double bond. Pi sigma negative charge. And since it is in conjugation, that means this negative charge electron is pi electron. It can be pi bond. That's why it is pi electron. Are you getting my point, Seth? Sigma electron cannot be sigma bond, pi bond. But since this is in conjugation, so this negative charge is pi electron. So we are going to count this, not count this in hybridization, and it is sp2. Complete conjugation is there, and 4 pi electron is there. Why 4 pi? 1 pi bond, 2 electron, 2 pi electron, and 1 negative charge, which is in conjugation, 2 pi electron. That's why 4 pi electron. And due to 4 pi electron, it is anti-aromatic. Is that clear, sir? Mamuna, Farhat. Now come to this cyclic, it is planar, it is conjugation, complete conjugation, pi sigma lone pair, pi sigma pi sigma lone pair. And if you are going to count the pi electron, you can see 2 pi bond is there and 2 electron, which is in conjugation. So 6 pi electron. That's why it is aromatic. Now you can think about this cyclic structure. Planar, it is all the carbon is sp2 hybridized, and this is in conjugation. Pi sigma vacant orbital, pi sigma vacant orbital. So this is in conjugation and it is aromatic. It is what? Aromatic. And if you are going to check this, this is also aromatic. Not aromatic, anti-aromatic it is. Why? You can see cyclic conjugation, planar, and how many pi electron? 4 pi electron. 4 pi bond. 2 pi bond is there, 4 pi electron. That's why it is aromatic, anti-aromatic. So it's very important. Please let me know if you face any kind of doubts in this. I'm waiting. Any doubt in this?
No, sir.
Okay, thank you. Moving to the next topic, that is hyperconjugation, also known as no sigma bond resonance. It is just like resonance, but this there will be delocalization of pi bond, sorry, sigma bond, and it is also known as Baker-Nathan effect. Now, complete transfer of sigma electron takes place, only applicable for carbocation, carbon free radical, double bond, triple bond, and phenyl system. How you are going to recognize whether which is hyperconjugation or not? So only this system will show hyperconjugation, and with respect to this system, we calculate alpha carbon and alpha hydrogen. See, like this is your alkene. This is your alkene, and you can see directly connected carbon will be alpha carbon. The carbon which is directly connected to this system, either cation, free radical, alkene, alkyne, and phenyl. That carbon are known as alpha carbon, and the hydrogen which is attached with alpha carbon is known as alpha hydrogen. So you can see three alpha hydrogen is here. Wait a minute. Three alpha hydrogen is here, three alpha hydrogen is here, and three alpha hydrogen is here. Total alpha hydrogen is 9 alpha hydrogen. In the same way, you can count the calculate the alpha hydrogen here. This is your carbocation, and you can see this is your alpha carbon, alpha carbon, alpha carbon. Each alpha carbon is having three alpha hydrogen. Total alpha hydrogen is 9 alpha hydrogen. With respect to free radical, you can see alpha carbon, alpha carbon, alpha carbon. So it also has 9 alpha hydrogen. You can see with respect to this carbocation, alpha carbon, alpha carbon. Each alpha carbon is having three alpha hydrogen. So total 6 alpha hydrogen. With respect to this, you can see alpha carbon and alpha carbon. This alpha carbon having only two hydrogen. That's why 2 alpha hydrogen, and this is total alpha hydrogen here will be 5 alpha hydrogen. With respect to this benzene group, you can see 3 alpha carbon is there, 1, 2, and 3. And 3, each alpha carbon is having 3 alpha hydrogen, so total 9 alpha hydrogen. With respect to this, you can see 1 alpha carbon is there, and with this alpha carbon 3 alpha hydrogen is there. So this is how we calculate alpha hydrogen, and this alpha hydrogen is very important because number of alpha hydrogen directly proportional to stability. If you remember, in the last class I introduced a question that is completely based upon this alpha hydrogen. That question was not completely answered with the help of inductive effect. That's why we deal with that, this alpha hydrogen. If a compound is having more and more alpha hydrogen, that means that is more and more stable. Is that clear, everyone? Please do let me know. Okay. So how many students are fasting today? I'm just asking for them. Please do write it and then let me know. Everyone done with this? Can I change the slide?
Yes.
Okay. Alan, are you able to understand all this? You are not replying at
Yes,
all.
sir. Yes, sir.
Okay. So this is not connected to any alpha carbon. So there is no alpha hydrogen, zero alpha hydrogen. This alkene is not connected to any other carbon directly. So it is also having zero alpha hydrogen. And here I have written as stability is directly proportional to number of alpha hydrogen. This is very important. If in a system you are having resonance, hyperconjugation, and inductive effect, all these three effects, then you are going to give preference to resonating structure or resonance. Resonance, you will give more and more priority, then hyperconjugation, then inductive effect. Okay, is that clear?
Yes, sir.
So can anyone tell me which one is more stable here? See, if you are going for alpha hydrogen, this is not benzene system, so you are having 3 alpha hydrogen. are going to take it as an alkene. This is your alkene. So with respect to this alkene, this is your alpha carbon and this is also your alpha carbon. You are not going to take this as alpha carbon because this is an alkene and you are having 2 alpha hydrogen and 3 alpha hydrogen. And if you are going to check this with respect to this, this is your alpha carbon and with this we have 2 alpha hydrogen. So total we are getting 3 plus 2 plus 2, that is 7 alpha hydrogen. Now with respect to this, you can see alpha carbon, alpha carbon, alpha carbon, and alpha hydrogen here 3, 2, and 2. How much it is? 5. Sorry, 3 plus 2 plus 2, 5. Sorry, 3 plus 2, 5 plus 2, 7. And with respect to this alpha carbon, we just counted it. So total 7 alpha hydrogen. Now you can think both the alpha hydrogen are same, but you can see here it is in conjugation pi, sigma, pi. That means in this compound, resonance plus alpha hydrogen is there, but there is no conjugation. You can see pi, sigma, sigma, pi. There is no conjugation. Only alpha hydrogen is there. That's why this is more stable than this. This is an example to show we give preference to resonance than hyperconjugation. Is that clear? Yes or no?
Yes.
Okay. I also have written here stability of alkene or a stability of carbocation or a stability of free radical or a stability of alkene alkyne, that is directly proportional to alpha number of alpha hydrogen. Always remember that we calculate alpha hydrogen with respect to free radical, carbocation, alkene, alkyne, phenyl, not carbon anion. We don't count alpha hydrogen with respect to carbon anion. Tell me which one is more stable. One ABC. In ABC, please tell me. Just do it. I'll be back. Any answer? How many alpha hydrogen in the first one? Three alpha hydrogen or 3 alpha carbon? See, alpha carbon, we don't go for alpha carbon, instead we go for alpha hydrogen. So with respect to this, we have 3 alpha carbon and each alpha carbon is having 3 alpha hydrogen. 3 alpha hydrogen, 3 alpha hydrogen, 3 alpha hydrogen. Very good. So total 9 alpha hydrogen. Now with respect to this, you can see only 1 alpha carbon is there and this has only 1 hydrogen. That's why 1 alpha hydrogen. Now with respect to this, you can see this is your alpha carbon that is directly connected and this is also alpha carbon which has 3 hydrogen here, that is alpha hydrogen, and 2 hydrogen is here, that is alpha hydrogen. So total 5 alpha hydrogen. Stability directly proportional to number of alpha hydrogen. So the most stable A, then C, then B. Very good. What about this? If you are going to check it, this is your alkene, this is alpha carbon, alpha carbon. It has 3 alpha hydrogen, it has also 3 alpha hydrogen, total 6 alpha hydrogen. And here if you are going to check 3 alpha carbon, 3 alpha carbon, but sorry, 1 alpha carbon, which will have 3 alpha hydrogen, 3 alpha hydrogen, total 6 alpha hydrogen. Both have same alpha hydrogen, but this is your cis. Same side bulky group, there will be repulsion, and this is trans, which means they are in opposite direction and there will be no repulsion. So trans will be more stable than cis. Is that clear, everyone? Yes or no?
Yes, sir.
Okay. Moving to the next topic, that is bond length. For bond length, you have to remember this. You know that single bond is the lengthiest bond, yeah, it will have more length, then double, and then triple. If multiple bond is there, that means it will have shorter both bond length. But you know that in resonance, what will happen? In resonance, some bonds are single and then double, single, double. So the lengthiest bond is single. Then comes your partial double bond due to resonance, partial double bond. And after that, pure double bond and then triple bond. Order of, this is the order of what? Bond length. The lengthiest bond length is of single, then partial double bond. As you can see, I'm talking about this. If you can see, this is your, let's say this is your chlorine. Chlorine has a lone pair, which is single, you can see, but due to resonance, there will be partial double bond character in this. This is your pure double bond. Okay. Can I change the slide?
Yes, sir.
Okay. Now, first of all, you need to take care of this. Lewis acid. What is Lewis acid? Electron pair acceptor. Electron pair acceptor is the one which is called Lewis acid, and Lewis base is the one electron pair donor. That is Lewis base, and this will be followed in our organic chemistry. Like if you have seen like this is negative, this is fluorine, and this is also fluorine, and this is O negative, and you can see NO2 is there and NO2 is there. So the compound which has more electron withdrawing group is there, then that will be more and more acidic. So NO2, 2 NO2 is there, 2 fluorine is there at same position, but this will be more acidic because NO2 is more powerful electron withdrawing group than fluorine. That's why this is more acidic. So there is a simple acidic character directly proportional to minus I, negative inductive effect, electron withdrawing group, minus R, or you can either write minus M, negative resonance or negative mesomeric effect, directly proportional to K. K stand for acid dissociation constant. Acid dissociation constant. If the value of acid dissociation constant is more, then that means it is acid. Inversely proportional to pK and inversely proportional to donating tendency. Acid is one which withdraw electron, and if there is a group that is donating, that will decrease its acidic character. And basic character is inverse of acidic. Basic character, you can see electron pair donor. So the group which is donating more and more, that will be more acidic and directly proportional to KB. That means base dissociation constant. Base dissociation constant. Inversely proportional to PKB. PKB is inverse of KB. That's why inversely proportional. And this is very important. Please do let me know when to change the slide. Can you change the slide?
Yes, sir.
No. Thank you. Can you see a new screen? Yes or no? So you are going to solve this question number 60 and question number 61. Any answer? $60, it's wrong, is it? 61, it's good. I'm going to explain the first one, 60. You can see RC negative, negative charge, that means electron rich species, as you can see, electron rich species. And it doesn't want any, basically it is electron rich species, it want to donate, and you can see this is your SP, which will withdraw and stabilize this carbon anion. This is negative, and you can see sp2 that will be withdrawing electron from here, and this will also be withdrawing so that it will be stable. Here you can see RCH, this will be withdrawing, only one withdrawing group, and this will be donating. So basically A will be the most acidic, most stable, because in this example negative charge is there, that means it is having electron rich, it is having more and more electron, and it wants to donate. It will not take electron because it is already having a lot of electrons. Electron pull out is increases, so easily will be withdraw by this sp, then this sp2, this is also sp2, but this sp2 is surrounded by r2, that means it will also donate. R is the group general inductive effect, or will be plus I. So A, then B, then comes your C, and then comes your D. So the answer will be A. And for 61, as you can see, wait a minute. 3 alpha hydrogen, 0 alpha hydrogen, 6 alpha hydrogen, 9 alpha hydrogen. So the answer is D. Is that clear?
Yes, sir.
So it's very easy. Okay, go for 68. I'm waiting. C will be the answer. Tertiary, 9 alpha hydrogen. There will be 3 alpha hydrogen, 6 alpha hydrogen, and so. We did this in the previous class, right? Question number 53. Yes or no?
Yes, sir.
Just wait a minute. I need to give you some question regarding. Okay. Question number 54. Please do it. Very good. Who gave this answer? Wait a minute. MS. Okay. So homolytic fission is there of an alkanes, ethane, propane, and you can see. So okay, 2-methyl propane, and then comes your 2-methyl butane. So this is your tertiary. This is your tertiary. Tertiary is there. The most stable tertiary, which will have 9-alpha hydrogen. Then comes your secondary. Then comes your secondary, because this will have more alpha hydrogen, and then this. So the answer is C. If anyone have any doubt, please ask me. I will be elaborating this with another method by writing all the structure. So please do let me know. Alan Hanifa, no respond at all. Mamuna, please do respond.
Yes, sir.
See, I'm gonna, if you are going to do the homolytic cleavage, it will be CH3 and CH2 dot. This is the first. The next one, homolytic cleavage has been done, and it will be basically in between like this. Then comes the next one, that is like this, C dot CH3 and CH. And then comes the next one, that is wait a minute, that is, yeah, C dot and CH2 is there, and CH3 is there, and then CH3 and CH3. So I told you to calculate the alpha hydrogen with respect to radical, carbocation, alkene, alkyne, and phenyl. So with respect to this, you can see 3 alpha hydrogen is there. With respect to this, you can see 3 plus 3, 6 alpha hydrogen is there. With respect to this, you can see 3, 3, 3, 9 alpha hydrogen is there. With respect to this, you can see 3, 3, 2. That means 8 alpha hydrogen is there. That means this is the most stable. So in option C, this is the scenario. Then 8 alpha hydrogen. then comes your 6 alpha hydrogen, and then comes your 3 alpha hydrogen. Is that clear? Can I change the slide?
Yes, sir.
Yes. Oh, wait a minute, please. These are all PYQs, previous year's question. I'm gonna give you the last question. The state of hybridization of benzyl carbonium. What is the hybridization of this carbon? It's very simple. See, two hydrogen is bonded with this. Very good, sir. And this is like this. Now, hybridization is equal to what? Sigma bond plus lone pair. No lone pair is there. 3 sigma bond is there. So if the sum is of the sum of lone pair plus sigma bond is 3, that means it is sp2. It's very easy. If you are facing this kind of problem, just let me know. Alan, Fatima, Mamuna.
No, sir.
Okay. Can you see a new screen?
Yes, sir.
Mamuna. Yeah. Alan. Okay. So let's start our aromatic compound. What is aromatic compound? As we already discussed, that the compound should be cyclic, the compound should be planar. There must be conjugation in all the ring, complete ring, and then follow Huckel rule, and that rule is for aromatic. We know that 4n plus 2 pi electron. That means 2 pi electron, 6 pi electron, 10 pi electron, and so on. So everyone knows that this is your aromatic and this is also your aromatic compound. Is that clear? So this is the definition, or how we are going to recognize about aromatic compound. This is the concept. Now we are going to start this MOP, that means methods of preparation of hydrocarbon, aromatic hydrocarbon, or basically the benzene. You have studied this every reaction in class 11th as well as in class 12. So first of all, how we are going to prepare benzene from N-hexane. N-hexane. It's very easy. See, this is your N-hexane, that is normal hexane. So if you are going to pass this through either Cr2O3, either Cr2O3 or Al2O3 or V2O5 or V2O3, you can write V2O5 or MO2O3, and the temperature pressure should be 10 atm and temperature should be 773 Kelvin. The temperature, this is pressure, this is temperature, and these are the reagent. Then this hexane will be directly converted into benzene. And if you want to prepare benzene from ethane, you need to pass this ethane from a red hot iron tube. A red hot iron tube. and you need to take 3 moles of ethyne. I'm going to explain this. CH triple bond CH. This is basically trimerizes. This basically trimerizes like this. This will go like this, and it will form benzene. If you want to prepare from phenol, you just need to pass it through zinc. Zinc is a reducing agent that will take oxygen with itself and it will be converted into benzene. From carboxylic acid or benzoic acid, you just need to do soda lime. You just need to pass it through soda lime. What is soda lime? NaOH in the presence of CaO. Sodium hydroxide and mixture of sodium hydroxide and calcium oxide. This will be removed. CO2 will be removed and hydrogen will again stick to this. That means it will be converted into benzene. If you want to prepare benzene from sulfonic acid or benzene sulfonic acid, you just need to pass it through warm water. Either you can do warm water or dilute H2SO4 or dilute H2SO4. Then you will be getting benzene. If you want to prepare benzene from benzene diazonium salt, you just need to reduce it with the help of H3PO2, or either you can take ethanol, ETOH, ethanol, and this will be acting as reducing agent. And this benzene diazonium salt or benzene diazonium will be converted into benzene. And if you want to convert it from, this compound is very important and famous, benzene, also known as BHC, benzene hexachloride, triple six. It is also known as 666. This is not benzene. Just be careful. This is not benzene. Basically, this is a hexachloride, cyclohexachloride. But its common name is benzene hexachloride. Its common name is benzene hexachloride. And if you want to prepare it from here to benzene, it's very easy. You just need to react this with zinc dust and heat it. What will zinc do? Zinc will double bond between this carbon and this carbon. Then another zinc will come and it will take it out, and then the double bond will come between this and this. Then another zinc will come and it will take it out, and there will be double bond between this and this. So it's very easy. Very easy. So this is the preparation of aromatic hydrocarbon or benzene in one go. Please do write it. Let me know when you are done with this. Alan, are you done with this?
Yes, sir.
Oh,
1 minute, sir.
okay. You have to remember the reagent. What does this reagent do? Basically, red hot iron tube, alkyne will be converted into benzene. You can use that to do that. This hydrocarbon directly converting into aromatic hydrocarbon. Zinc will be, if you are going to react this with phenol, it will reduce it to benzene. This is basically carboxylic acid. If you want to convert it into hydrocarbon or aromatic hydrocarbon, you can do this. SO3H, warm water, SO3H will be removed and it will be converted into benzene. BDS, just use this to reduce it and it will be converted into benzene. This is important. Gamoxene, BHC. Benzene hexachloride, please do write it. Because for benzene, students search for the bond, double bond. Saif, are you done with
Done,
this?
sir. Done.
Okay. Please do this reaction. If you understand the previous one, please do this reaction. When zinc react with alcohol phenol, what it will do? It will take oxygen from with itself, and this phenol will be converted into toluene or methyl benzene. You can see if this will be reacting with warm H2O, then it will be converting into CH3. This SO3H will be removed. SO3. Is that clear? So if you know the principle of this reagent, what does it actually do? The reaction cannot be wrong. It will be always right. Okay. Can I change the slide? Alan,
Yes, sir.
Mamuna. Okay. Now see chemical properties of aromatic hydrocarbon, in which the first reaction I'm going to tell you is about electrophilic addition reaction. Electrophilic addition reaction, and we are going to add HBr in this benzene ring. To add HBr in this benzene ring, we have to break one of the bond, because carbon is already making 4 bonds. So if you are going to break this bond, one of the bond, double bond of benzene ring, then what will happen? One of the bromine will go at any place and hydrogen will go at any place. So it is like this. And let's say bromine is here and hydrogen is here. But always remember, electrophilic addition reaction will not be shown by aromatic compounds. Aromatic compounds. Why it is so? Because you can see here it is aromatic. Aromatic, that means it is stable, and here it is non-aromatic. It is non-aromatic. That means it loses its aromaticity. Non-aromatic. That means it loses its, because it loses its aromaticity. That means stability. That's why this aromatic hydrocarbon does not show. Please remember that. Electrophilic addition reaction will not be possible in this reaction. Okay. Electrophilic substitution reaction is possible, but addition is not possible. Please do write it. Are you done with this? Can we move to the next part?
Yes, sir.
Okay. Now, the next chemical properties is electrophilic substitution reaction. Just wait a minute. Let me. Okay. Mhm. The next reaction is electrophilic substitution. Electrophilic substitution reaction. Or either you can do electrophilic aromatic substitution reaction. It is possible in aromatic compound. Why it is so? You can see this is your benzene ring, and you know this is your hydrogen. And to do electrophilic substitution reaction, there are two substances. One is electrophile, that will substitute, and another will be base. Another will be base. What will happen here? It's very easy. This hydrogen will be replaced by this electrophile, and you will be getting this. You will be getting this. But always remember, I have written this reaction in a single step, but this is not true. Basically, if you will go through mechanism, you will understand it will not be in a single step. This is your benzene, in which first electrophile is going to attack. First electrophile will go and attack on this alkene, because alkene will be also treating as, we also treat alkene as nucleophile, and this will be your slow state. Slow state, that means a rate determining state. Wait a minute. A rate determining state. So as you can see, are you able to see the screen?
Yes, sir.
There is a hydrogen, and this will be attacking at that place. That means this bond will be broken. This bond will be broken. So there will be positive charge, and there is a hydrogen already, and this positive charge electrophile will be going here, because since there is positive charge, so there will be negative charge that will satisfy this electrophile. After this, see what will happen. This benzene ring, that is not benzene right now, to stabilize itself, it will take electron from hydrogen and it will release hydrogen. It will release hydrogen and it will again gain its aromaticity. See what happens. First, it is aromatic and it loses its aromaticity for a while. That's why it is slow step. Whenever a more stable product will go to a less, that means it will loses its aromaticity, that means it loses its stability, and then again gain the stability or aromaticity. So that's why this is fast and this is slow, and this is how electrophilic substitution reaction take place, or electrophilic aromatic substitution takes place. Aromatic substitution takes place. Is that clear? So any electrophile, wait a minute, any electrophile, if this is the benzene ring and if you have an electrophile, it will attack at any position. You just need to recognize which electrophile it is and it can attack at any position. Just let me know when you are done with this. Let me know when you are done with this.
Done.
1 minute, sir. Done, sir.
Okay. Now see the next chemical properties. I'm going to show you this electrophilic substitution reaction. What you need to remember. Have you heard of nitration, halogenation, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylation? Yes or no? Just let me know, please. See, you have to keep the reagent in mind when concentrated HNO3, and concentrated H2SO4 are together, they will be reacting with each other. They will be reacting with each other and forms an electrophile, that is NO2 plus. We just took an example of E plus, and E plus will just substitute one of the hydrogen from benzene ring. So what will be our product? You can see by the combination of concentrated HNO3 and concentrated H2SO4 and E, we got an electrophile of NO2 plus. So NO2 go and attack on the benzene. Again, you can see this is a reagent. When you are going to heat it, you will be getting an electrophile, that is X plus. That means halogen. What you will be getting? You will be getting X plus, and this X plus will directly attack on the benzene ring, and it will be like this. With this concentrated H2SO4, either you will be getting SO3 neutral electrophile, or either you can get SO3H, you can get like this. And since this is an electrophile, so it will also attack on the benzene ring. And you can see this is RH in the presence of anhydride AlCl3. From here you will be getting R plus. R plus is the electrophile, and it will attack on the benzene ring. Since benzene ring is empty, that means basically only the benzene ring is there. There is no group that is attached with in benzene ring. if there is any group, if there was any group, then with respect to that group, we add that at ortho and para. Like this, you can see this is your electrophile. This is your electrophile. So it will be attacking on the benzene ring. You are aware of all this reaction. You are aware of all this reaction because you have heard that this is nitration. Nitration, that means addition of nitro group. This is your halogenation. Addition of halogen. We are phonation. This is your Friedel Craft alkylation. Friedel Crafts alkylation. And this is your Friedel Craft acylation. Friedel Crafts acylation. Let me know when you are done with this. Everyone done with this? Alan, Farhad, Hanifa, Mamuna, Saif.
Yes, sir.
Yes, sir.
Yes, sir.
Now please do this. I'm going to explain one of this and then you are going to do it. First, you are going to recognize this. This, you know what it is. It will generate a electrophile, that is NO2 plus. And since one group is there, so this NO2 plus, which is an electrophile, that will be adding at ortho and para only. You know that CH3 is plus I effect. So with respect to CH3, this NO2 will be here and this NO2 will be added. You just need to recognize the electrophile with the following reagent, and this will be your measure. Please do the rest. Everyone done with this?
Yes, sir.
So what is the product from here? You can see you have got the X plus. So this will be the product with respect to CH3. X will come here, halogenation it is. And with respect to this, we have this. Seth
Yes, sir.
and Alan. So this is about your aromatic hydrocarbon. Please do this last question. This is your homework, just write it. And in the next class, we are going to start, what we are going to start is, what we say, wait a minute, alkyl halide in the next class. Please do a quick revise at your home and also try to do questions on that and also deal with the PYQs. Let me know when you are done with this. This is your homework. Okay.